In the skies of tomorrow, aircraft won't roar with burning fuel or leave behind trails of carbon emissions. Instead, they'll hum softly, propelled by invisible streams of charged air. Imagine flying halfway around the world without a single drop of jet fuel, powered only by the ionization of the atmosphere itself. This is the promise of atmospheric ion engines, one of the most fascinating frontiers in propulsion science. At first glance, the concept sounds almost magical, flying machines that glide through the air using nothing but electric fields and ions. But beneath the wonder lies a foundation of real physics. An atmospheric ion engine works by generating a powerful electric field that strips electrons from air molecules, creating ions. These ions are then accelerated backward, producing thrust in the opposite direction. It's Newton's third law. For every action, there's an equal and opposite reaction, applied to charged particles. This method of propulsion isn't entirely new. In fact, the earliest form of ion propulsion was used in space decades ago. NASA's Deep Space One probe, launched in 1998, used a xenon ion engine to travel millions of miles across the solar system. But there's a key difference. Space ion engines work in a vacuum using inert gases like xenon, while atmospheric ion engines generate thrust by directly ionizing the air around them. That's a massive leap, one that could change everything about how we move through Earth's atmosphere. At the heart of the system lies a simple yet revolutionary principle: electrohydrodynamic thrust, or EHD. When a high voltage is applied between two electrodes, a thin wire and a thicker collector, the air molecules near the wire become ionized. These positively charged ions rush toward the collector, colliding with neutral air molecules along the way. Each collision transfers momentum, pushing air backward and generating thrust forward. The process produces no combustion, no moving parts, and almost no sound. It's propulsion in its purest form, air accelerated by electricity alone. In 2018, researchers at MIT, led by Professor Stephen Barrett, demonstrated the first fixed-wing aircraft capable of sustained flight using nothing but ion propulsion. The plane weighed around 5 pounds, had a 5-meter wingspan, and carried lithium polymer batteries powering a series of high-voltage converters. As it glided silently across a gymnasium, it marked a turning point in aviation history. It wasn't fast or powerful, but it proved that ion-based flight within the atmosphere is possible. That experiment was just the beginning. Since then, laboratories and startups around the world have been working to improve the efficiency and scalability of atmospheric ion engines. The biggest challenge lies in thrust density. Conventional jet engines produce enormous amounts of thrust because combustion releases immense energy. Ion engines, in contrast, generate very little thrust per unit area. To lift larger aircraft, engineers need stronger electric fields, better ionization methods, and lightweight materials that can handle high voltages safely. One promising direction involves plasma-assisted designs. By combining ionization with small plasma discharges, these systems can dramatically increase thrust output while maintaining the quiet, emission-free nature of ion propulsion. In such setups, plasma jets can be used to energize airflows or even work in tandem with turbines, creating hybrid propulsion systems that use less fuel and produce less noise. The potential advantages of atmospheric ion engines are staggering. First and foremost, they offer true zero-emission flight. Unlike combustion engines that burn hydrocarbons and release CO2, ion engines rely on electric energy that can be sourced from renewables like solar, wind, or fusion power. Second, they have no moving mechanical parts, which means fewer breakdowns, less maintenance, and near-silent operation. Imagine airports without deafening noise or vibration. Third, they could open the door to ultra-efficient long-endurance drones, surveillance platforms, and even passenger aircraft that cruise at high altitudes where air is thin but stable. But how would such an aircraft perform in real-world conditions? That's where design innovation comes in. Engineers are exploring electrode geometries that optimize ion flow, from thin wires to grid patterns that can accelerate ions more efficiently. Materials like graphene and carbon nanotubes are being tested for their high conductivity and minimal weight. Some researchers envision entire aircraft surfaces doubling as ion thrusters, wings that are themselves engines. This integration could eliminate the need for separate propulsion units altogether, creating smooth, aerodynamic vehicles that glide effortlessly through the air. Energy supply remains another key challenge. Current prototypes rely on onboard batteries, but for long-distance travel, other energy sources are being considered. Wireless energy transmission, where power is beamed to aircraft from ground stations or orbiting satellites, could one day keep ion-powered planes aloft indefinitely. Another possibility is to pair ion engines with compact nuclear or fusion power cells, delivering immense electric potential without heavy batteries. The physics of ion propulsion also opens fascinating possibilities for high-altitude and near-space flight. At altitudes above 60,000 feet, the air becomes thin, but an ion engine can still function. In fact, it might perform even better due to reduced drag. This could allow for aircraft that skim the edge of space, operating in regions too high for jets and too low for orbiting satellites. Such vehicles could serve as communication relays, atmospheric research platforms, or rapid global transport systems capable of reaching any point on Earth within a few hours. One particularly exciting concept is the ion glider hybrid, an aircraft that uses engine propulsion to generate forward thrust while using aerodynamic lift to stay airborne. It could take off from a runway using electric thrust alone, climb silently to the stratosphere, and then cruise efficiently across continents with minimal energy expenditure. Imagine airliners that never refuel, never emit pollution, and produce only a gentle hum, the sound of charged particles moving through air. Of course, no new technology comes without hurdles. The power requirements for ionization are immense, often reaching tens of thousands of volts per meter. Managing that safely in variable weather conditions, especially in moist or stormy environments, poses significant engineering and safety challenges. Arcing, corona discharge, and material degradation are all risks that researchers must overcome. But each year, advances in insulation, voltage control, and materials science bring these hurdles closer to resolution. Then there's scalability. While small drones and experimental aircraft are already testing ion propulsion successfully, scaling the technology to large passenger jets or cargo transports will require breakthroughs in energy density and thrust efficiency. Hybrid approaches might lead the way, using ion engines for low-speed, quiet operations like takeoff and landing, and conventional or plasma engines for high-speed cruise. Over time, as electric energy systems improve, the balance could shift fully toward ion propulsion. Even today, the potential applications extend far beyond aviation. Atmospheric ion engines could revolutionize underwater propulsion by replacing propellers with silent, bubble-free ion drives. They could be used in windless drones that hover steadily for days, ideal for environmental monitoring, agriculture, or disaster response. And in architecture, similar principles could enable floating structures or hovering transport pods supported by ionized air currents. Looking further ahead, atmospheric ion technology could also serve as a stepping stone to planetary exploration. Mars, for instance, has a thin atmosphere of mostly carbon dioxide, a perfect medium for ionization. Future Martian drones or aircraft could use local air to generate lift and thrust, powered by solar or nuclear energy. Unlike traditional rockets or rotors, ion engines could provide sustained, silent operation for mapping, surveillance, or cargo delivery on alien worlds. But perhaps the most profound impact of atmospheric ion propulsion will be psychological. Humanity's relationship with flight has always been noisy, fiery, and turbulent. We associate power with sound, the thunder of rockets, the scream of jets, the roar of engines. Ion propulsion challenges that perception. It introduces a new aesthetic of motion, smooth, clean, and almost serene. It represents a shift from brute force to elegance, from conquering the sky to coexisting with it. If this technology matures, it could redefine what aircraft look like. Forget about turbines and exhausts. Imagine sleek, seamless crafts with luminous edges glowing faintly blue as ions accelerate through the air. These vehicles wouldn't just fly, they'd glide in harmony with the atmosphere, powered by the very air they move through. The societal implications could be enormous. Noise pollution around cities would vanish. Air travel could become dramatically safer and more sustainable. Airlines might one day offer truly green flights, where passengers soar quietly above the clouds, knowing their journey leaves no trace on the planet below. And for the first time since the dawn of aviation, humanity could master the art of flight without burning a single drop of fuel. In many ways, atmospheric ion engines symbolize a turning point, a transition from the mechanical age to the electrodynamic age. It's an echo of the same transformation that took us from steam to electricity over a century ago. And just as early electrical experiments once seemed impractical, today's ion propulsion research is laying the groundwork for a revolution that may define the skies of the next 100 years. As artificial intelligence, nanotechnology, and advanced materials continue to evolve, the pace of innovation will only accelerate. AI models can now optimize electrode designs and airflow patterns faster than any human engineer. Nanomaterials like graphene are pushing the limits of conductivity and heat resistance. And as new energy sources emerge, from compact fusion to orbital solar stations, the dream of fully electric, self-sustaining flight draws ever closer. The future of flight may not be about speed alone, but about silence, sustainability, and grace. A new kind of flight that aligns with the Earth's natural rhythms rather than fighting against them. Atmospheric ion engines are not just machines. They're a vision of harmony between humanity, technology, and the air we breathe. So when you look up at the sky decades from now and see a plane gliding soundlessly, leaving no trail, you might be witnessing the dawn of the next era of human motion, the age when we finally learn to ride the charged winds of our own atmosphere. And the quiet hum you hear won't be an engine's roar. It'll be the sound of progress itself. Hey everyone! If you enjoyed this video, make sure to hit that like button, drop a comment to share your thoughts, and subscribe so you don't miss any of our future uploads. Your support helps this channel grow. Thank you for watching.